Welcome to the fourth lecture of module 5. In this lecture today, we shall focus on the metal wire additive manufacturing and particularly by using the MIG welding process. So, our today's content is going to be the introduction to the deposition process for the metal wire additive manufacturing, and particularly it will be focused on the MIG welding process. Then we shall discuss the most popular welding process used in additive manufacturing for MIG, that is called as cold metal transfer, and I will discuss then about the process cycle. After that, I will discuss about some of the process parameters involved and then geometric modeling, where we will cover about the single bead modeling, multi-bead XY deposition modeling and multi-bead modeling in Z direction. Then we shall discuss about the material properties, that will include a brief discussion about the hardness and strength we obtain in the part fabricated by this process, and then the major type of defects which we usually get by WAAM. Those are popularly the residual stresses, porosity, crack and delamination. And then in the end, we shall discuss about the different variants of the 3-axis, 5-axis, serial, parallel and hybrid kinematics of wire arc additive manufacturing. So, if you recall our classification, we were discussing mainly now on the materials when the metal wires are used. If the metal wires are used and the deposition is happening continuously, not in the drops or the drop on demand, which we discussed earlier for the case of polymer developed by a system by Arberg. So, that such cases are not really available for metal, and on the machine side it can be a serial kinematics, it can be parallel kinematics, or it can be a hybrid kinematics. Then the energy source, our focus in this lecture will be now on the energy source when it is arc. When arc is the energy source and metal wire is the raw material, then the process is also called as wire arc additive manufacturing and popularly nowadays known as WAAM. Now, there are different options available for generating the arc. It could be the MIG welding process, it could be the TIG welding process, or it can be the plasma arc welding process. Therefore, the focus of this lecture will be primarily on the MIG welding based process. We will discuss later on about the TIG and plasma also. If we are using arc as the energy source to create the molten pool or to melt the wire, then there are two possible options for the support mechanism. Either we do not use any support at all, or we tilt the part appropriately to eliminate the need for support, and that is called as multi-axis kinematics utilized to tilt the part. So, as the MIG welding process is the heart of the WAAM, let us start our discussion with the fundamentals of the MIG welding process. In the MIG welding based wire arc additive manufacturing process, a MIG welding gun is used to add the material on a substrate or a pre-built layer. The metal inert gas welding, or more often called as gas metal arc welding, utilizes a consumable electrode, and hence the term metal coming into the picture. There are other gas shielded arc welding processes utilizing the consumable electrode, such as the flux core arc welding, and all of these variants of the consumable electrode type of process falls into the category of the MIG welding, the metal inert gas only. So, a typical setup for MIG welding based wire arc additive manufacturing is shown here in this diagram. So, usually the consumable comes in the form of a spool, as you are seeing here. So, this is the wire reel where the consumable is winded on. This wire is fed continuously into the welding torch, and that is written here. The welding torch is connected to a gas supply cylinder which provides the necessary inert gas. So, you can see that this is the supply for the inert gas, and when the wire is coming out from here and creating the arc, this shielding gas provides the shield to this molten pool to protect it from the outside gases such as oxygen and prevent it to get oxidized immediately. The electrode and workpiece are connected to the welding power supply, and the power supplies are always, in this case, are of constant voltage type. Let me discuss a little bit about this first. So a constant voltage type means this is the typical characteristic of the power source for MIG welding. If this is voltage and this is current, it is more like a flat curve. Why this? Because in the MIG welding we use a consumable electrode, right? And if we use a consumable electrode and it is creating arc. Now if the wire is coming down and assume that it just touches the substrate, in that case the voltage will drop down drastically, right? So for example, you are at this location and as the arc length is changing, the voltage is decreasing drastically. As a result, you see there will be a huge difference in the current, and current will increase very high rapidly. Basically, as the current will increase, it will melt the wire and it will break the connection between the wire and the substrate. As a result, the arc will further or once again maintain. So that is why usually the constant voltage power supplies are used in the case of MIG welding process. The current from the welding machine is changed by the rate of feeding of the electrode wire. So if the rate of wire feeding is changing, then of course the current supplied will also change. So in other words, this current supply is usually directly proportional to the wire feed. That is VW I am writing right now. It will be helpful for our further discussion. So the main requirement in WAAM system is the source of electric power. There could be two possible sources of electric power. One could be the DC welding source or it could be the AC welding source. If it is DC welding source, so DC welding is generally preferred because of the control of heat input offered by it. About 70% of the heat is liberated near the anode, right? Anode where the positive polarity is given. Hence, if more heat is required at the workpiece side, then the workpiece can be anode. And it is also called as straight polarity, we know that. Or in other words, it is also called as DCEN, direct current electrode negative. In that case, let us consider this case here. There is an electrode and this electrode is connected with the negative polarity, DCEN, right? Direct current electrode negative, and the substrate is positive, that is anode. Now the electron will come from this end and they will move towards the substrate. As a result, as more electrons will travel towards the substrate or the workpiece, more heat will be generated on this side. As a result, a greater penetration will be obtained. However, in the case of WAAM, we may not really require a very high penetration on the substrate and we may require a minimal penetration on the substrate. Therefore, in that case, we may use the DC reverse polarity. In the case of DC reverse polarity, if this is the electrode, the polarity of the electrode is positive. That is also called as DCEP, direct current electrode positive, and the substrate is negative. Now in that case, more heat will be generated on the electrode side and electrode will consume with a very fast rate, but the same time we may not get enough penetration into the substrate. As there will be less penetration, or in other words, it can be called as less dilution in the substrate, the feature can sustain which you are depositing on the substrate. Therefore, in the case of WAAM, it is usually preferred to use this polarity, means use the reverse polarity or DCEP. However, if you use AC, means the alternating current machines, in that case 50% heat will be generated on the electrode and 50% heat will be generated on the substrate. In that case, you will get the optimal penetration as well as the deposition rate as compared to the both possibilities we discussed earlier. Also, sometimes AC polarity is required for the material in which the oxide layers are formed and difficult to break, like in the case of aluminium. In the case of aluminium, when the polarity get reversed, means the electron travels from the workpiece towards the electrode, In that case or at that time, the oxide layers got break, and hence in the next cycle when the electrode become negative, more heat get generated onto the substrate. So this reversal of the polarity is very much important when you deal with such material. Those immediately create the oxide layers, and the melting point of those oxide layers are quite high. However, for the conventional steels, DC current is sufficient enough. Now let us discuss that how the material is transferred from a MIG welding source to the substrate. There are possibly 5 different metal transfer methods. The first one is the short circuit method, the second is globular method, and the third is the spray method, fourth is the pulse spray, and the last one is the rotating spray. Those are listed here. So when the material is transferred from the electrode towards the substrate, usually on that mainly 2 forces works. The one is the Lorentz forces, and the another is the gravitational forces acting due to the weight of the droplet form. As I have already mentioned, these are the 5 possibilities of metal transfer in the case of MIG welding. There could be few more, but those are the most popular ones. So when I talk about the short circuit, the deposition rate is approximately of 0.9 to 2.7 kg per hour. And if we go beyond, then you can see the deposition rate keeps increasing, except the case of the pulse, because in the pulse something different happened that I'll explain you. But as you can see in the rotating spray further, the deposition rate keeps on increasing. Also, the current rates also varies from top to bottom, and it is highest when it comes to the down. It is lowest for the short circuit. So this slide explains each and every process. So this slide can give you an idea of how the material is transferred in each and every discussed method. The first one is the short circuit metal transfer. As you can see, in the case of short circuit metal transfer, the wire is coming from the top and it is making a short circuit with the substrate, meaning to say the voltage drop down to 0. As the voltage drop down to 0 or very low value, of course we have seen the current suddenly increases. As a result, as the current increases, the wire gets melted and deposit the material into the substrate. So here each time the short circuit is happening. The another one is globular metal transfer. In this case, the current is slightly higher than the previous case, and the globular of the metal will be formed at the tip as you are seeing here. Under the gravity, then this droplet will fall down. Of course, it will get influenced by the Lorentz forces also, and the droplet will not just fall vertically, it will follow a trajectory appropriately. Similarly, in the case of spray metal transfer, the current is further high and the other forces are more dominating. Now you can see the metal is transferred in a spray like manner. Also in this case, the current is higher than the last 2 cases. The fourth one is the more optimal, is called as the pulse metal transfer. In this case, we do not maintain the constant value of the current, while the current varies in pulses like this, like I am showing here. This value of the current, which is at the lowest, is called as the background current, while this current which is on the top is called as the peak current. The benefit of the background current, or the purpose of the background current, is to maintain the arc, and the purpose of the peak current is to generate the droplet. So as you can see here in this video, the arc is generated and it is maintained. So when it is maintained, the current is low, and when it is glowing in the video, at that time it is detaching a droplet towards the molten pool, right? So in this manner, the average current is maintained at a very low value, and hence the heat transfer will also be less. as a result you will get a very optimal penetration into the bead, and also the material transfer to the substrate will be maintained. Further, if you increase the value of current from the spray metal transfer, the other mode of transfer, metal transfer, are like rotating spray metal transfer. In this case, the electromagnetic forces are more dominating, and as you can see also, the metal is transferring while rotating and hence transferring the material in a spiral manner towards the molten pool. In such cases, with the same current, the penetration reduces, but at the same time the width of the bead deposited increases drastically. So in the case of the wire arc additive manufacturing, the pulse mode of the metal transfer is the most popular one due to the advantages associated with it, such as the average power in this case is lowest as compared to the other mode of the metal transfer, and as a result you deposit the bead at a very low temperature. However, further the process came into picture is called as CMT and became more popular in the case of wire arc additive manufacturing. It is mainly due to the low heat input characteristics of this process. So the primary principle of the CMT is very much similar to the pulse mode of the metal transfer, but here the only difference is when the wire comes and it do the short circuiting with the substrate, instead of increasing the current like we do in the case of pulse transfer, here the wire itself is moved back. So the detachment of the drop is not done here by the increasing the current like we do in the case of pulse transfer, while here the droplet is detached by pulling the wire back. So the typical process is shown here in this diagram. So initially when the arc is initiated, the filler material moves forward, right, and it moves towards the molten pool created on the substrate. As the current is less in this case, right, so in this case current is quite low, the filler material will dip into the molten pool because it is not getting enough current to get melted, and as a result the arc will distinguish in this case. Therefore, the welding current is lowest to the smallest value in this case. So in this case the current is like very low. Now, like in the conventional process, to detach the wire from the substrate, we increase the current at this stage, and then the wire get detached and leaves a droplet on the substrate. Unlike that, now in the case of CMT, we move the wire backward. So as you are seeing in the third step. So a retracted motion of wire then assists the droplet detachment during the short circuit. Unlike in the conventional pulse arc where the droplet is notched by the current impulse. So mechanically, basically the droplet is left behind on the substrate. Once the desired gap is obtained, again the arc will be established and the process will repeat itself. So in this case, as we are not giving any impulse current to detach the wire, the average power is maintained at a very low value, and the process is very efficient and also can deposit the material at a very low temperature. This process found very much suitable for depositing the material such as aluminium. This is a typical video of how the CMT works. The slow motion of the CMT process can be seen from this video. Here we can see when the short circuit happens, the wire is going back. So it is pulled back by a mechanism, and as a result it leaves the droplet behind. So this is how basically the CMT works. Now let us come to the process cycle. So like other additive manufacturing process, in the case of wire arc additive manufacturing as well, we start with the CAD model. We generate its STL file, do the proper orientation, and then if possible generate the support. However, this step is redundant in the case of metal wire additive manufacturing because usually we do not provide the support. We have seen the case in our last discussion for the SDM, shape deposition modeling, where if you are depositing stainless steel, copper can be as the support mechanism. However, let us not consider the case right now for the WAAM and assume that there is no possibility of generating the support. And then we do the slicing and generate the tool path. After generating the tool path, we go for the deposition, and if required, we do some in situ processes such as rolling, pinning, hammering or interpass cooling. Then if required, we also perform a face milling operation, which is essential sometimes when there are a lot of oxide got scaled up on the top surface. However, this option is also not necessarily required all the time. Then finally, after generating the near net shape, so from this process we generate a near net shape, and that near net shape is then transferred to a milling machine, and the further milling operation can be performed to obtain the final desired surface finish. If required, we also do some heat treatment, and then finally we generate the component. So this operation nothing but falls into the category of pre-processing. This operation falls nothing but into the category of the in situ processes, and these operations falls into nothing but in the category of the post processing of the wire arc additive manufacturing. So the typical process parameters affecting the wire arc additive manufacturing process are listed here on this slide. The first one is the power. The power is governed by the arc voltage, starting, main and reduce and final current. So voltage and current are the two parameters, those are governing the power input to the substrate. Then the type of filler material. Which type of material we are using, what is the diameter of the wire, and what is the wire feed rate. Also it can be noted that the wire feed rate is usually in the case of MIG welding process, or the automatic, at least in the case of automatic MIG welding process, is directly proportional to the current which we are supplying. So they both are in synergy. Then the parameter associated with the gas, like what is the proportion of the gas, what is the gas pressure, flow rate, pre-flow period and the post-flow period. Pre-flow and post-flow period are nothing but before starting the welding or the deposition of the material, and after completion of the deposition of material, for how long the gas was switched on. Then the parameters associated with the deposition, like what will be the layer thickness, what will be the bead width and what will be the bead height. These are the important and the geometric parameters, those will govern the final accuracy of the part you are producing. Then there are some parameters associated with the torch or the deposition torch. Those are like distance between the nozzle and the base plate, that is also called as sometime as standoff distance. Then the distance between the contact tip and the base plate, that is nothing but the arc length, and then the torch speed by which you are depositing the material while the torch is traveling in one direction, or the traverse speed. Of course, another important parameter affecting the process is the path, in which path you are moving. There are two important parameters here, that which type of area filling strategy we are using, which we have already discussed in our CAPP module, and then the step over increment. Step over increment is nothing but the distance between the two consecutive passes, that is this step over. So how much should be this value? So usually whenever you are going to deal with a new material, it is recommended to perform 3 experiments. The first one is called as single bead experiment, and by the single bead experiment we usually measure 3 parameters. One is the height of the bead, depth of the bead and the penetration of the bead into the workpiece. Then after that the multi-bead experiment is performed, where we try to find out the optimal step over or the distance between the 2 consecutive beads in such a way that you obtain a nearly flat surface on the XY plane. Also sometimes we deposit one bead over another bead and keep on depositing in Z direction, and in that case we try to find out what is going to be the height at a particular value n of the when the layer is deposited. So this falls into the category of when we study the multi-bead deposition. After multi-bead deposition, one has to study the multi-layer deposition, and then one can characterize and find out the different material and mechanical properties of the deposited material. So these experiments are shown here. The first I said is like single bead experiment. Multi-bead experiment can be in two directions, that is what you are seeing in this image is corresponding to the XY direction multi-bead experiment, or it could be the deposition one over another, and that I will call as multi-bead in Z direction. Then multi-layer comes after the XY deposition, where we deposit multiple layers like this, and after completion of multi-layer deposition we have the final component, and that can be used to further characterize and get the material and mechanical properties of the part. So now let us discuss about the geometric modeling. We deposited a bead, right, and we are trying to now find out what will be the width of the bead if we are going to measure its height. For that, we will first assume that our bead which we are depositing is getting a shape of parabola. If we are assuming that the shape of the bead is parabola, and we are also assuming that this is the origin which is here 0, 0, and this is x-axis and this is y-axis. So what you are seeing is a cross section of the bead while you are depositing in this direction, right? You are depositing in this direction, and what you are seeing is a cross section. Now in that case, I can write the equation of this curve which I assume to be a parabola, this one, as y equals to a plus cx square. The maximum height of this parabola will be nothing but the bead height, and the width of this parabola on the substrate will be nothing but the bead width. Also, some of the portion of the substrate will also get affected, and that will be called as the penetration depth. So now try to find out these constant A and C in terms of the bead width and height. So as you know that this equation y equals to a plus cx square is the equation of parabola, I can put the boundary conditions here. Like I know that at x equals to 0, that is at the center at this location, the value of y is maximum, and that is nothing but the height of the bead, and that is h. If I put that value here in this equation, I will get a equals to h. Also I know that when y is equals to 0 means, so at y equals to 0, meaning to say at this location or on this axis where everywhere y is 0, the value of x, if you observe on this curve only, the value of x is nothing but this much, and that is half of the width. I am calling it as w by 2. So at y equals to 0, x is equals to width by 2. As a result, you can find out the value of the constant c, that will be equals to 4h by w square. Now I can put these two constant back into that equation, and as a result I will have the equation which is representing the shape of the bead as y equals to h bracket 1 minus 2x by w square bracket close. Now this is preferable to write the same parabola in terms of the process parameters also. Right now what you are seeing here is h and w. So it is preferable to write the same parabola in terms of the process parameters, and the process parameters are the wire speed and the torch speed. We know that this wire speed will be directly dependent on the current, and that curve we usually have, and we can easily find out the wire feed or the wire speed based on the given current for the machine. So how can we incorporate these two variables into this equation? So for that, let us first try to find out the area of the bead deposited. So as we are depositing a parabola like this, which is having height h and width from this point to this point w by 2, and the total width is of course w from here to here. In that case, the area of this region will be equals to 2 by 3 h into w, that is the area of this parabola or the bead. If this is the area of the deposited bead and we are depositing with the speed of Vt, right, that is the torch speed, this one, then the volume flow rate will be equals to area A into Vt, right? Or let me write it here. I can write it as Q equals to the area, that is 2 by 3 HW into Vt. Also the wire is coming, right, and the wire diameter is assumed to be D, and this wire is coming with a speed, or wire is coming towards the molten pool with a speed Vw, that is the wire speed. So the volume rate of the wire input into the molten pool will be equals to, I am writing here Q equals to the area of the cross section area of the wire, that is pi by 4 d square multiplied by the velocity of the wire, that is Vw. Now both these values should be equal, because the volume flow rate coming towards the molten pool and the volume flow rate that is corresponding to the deposition of the bead should be equal. As a result, you can easily find out the value of W if you just equate these two equations, and W will be equals to 3 pi Vw d square divided by 8 HVT. Now from this equation I can replace the value of W in the equation we derived for the shape of the bead. Now as you can see, the equation is a function of the process parameters Vt and Vw both. However, this is a very simplified version of finding out the shape of the bead. The formation of the bead usually interplay of several physical phenomena such as gravity, electromagnetic force, viscosity, surface tension, etc. That part we have not considered here. Therefore, although both H and W depend only on the process parameters, obtaining their relationship in terms of them is too difficult, as it would involve modeling of all these phenomena, those I mentioned here. Therefore, the above equation is a hybrid form of parabola that includes the easily measurable geometric parameters, and that is nothing but H. When you deposit a bead, you can easily measure it by using a vernier caliper. Once you know the value of H and you are assuming that the deposited bead is a parabola, you can find out the other values corresponding to that. So once we know the value of H on the deposited bead, you can easily find out the shape of the bead by utilizing this equation. Also, in that equation which we have seen just now, there was a term Vw. The wire feed is not easily measurable in the case of the machines where the wire feed is in synergy with the welding current, and that is true for most of the automatic MIG welding machines. However, we used to get a linear curve between these two, meaning to say Vw is directly proportional to the current we are supplying to the machine. However, this curve can be different and it has to be calibrated whenever you buy any new machine. So what you are seeing here, the current versus the wire speed, that is Vw, and here is the current. So if I am using a current, for example, of 100 amps in my machine, then I can see the corresponding wire feed at that, the value of the wire speed will be 8.5 meter per minute. So once we obtain the shape of the bead deposited by the single bead experiments, now our task will be what should be the optimal step over between the two consecutive deposition, so that I can obtain approximately flat surface on the XY deposition. So that will be called as multi-bead deposition in the XY plane. So for example, this is the first bead we are depositing and this is the second bead. In that case, there will be three cases. One is that your overlap is optimal and the final shape which you are obtaining is having a flat surface here. In that case, the volume of this region, I am writing by A, will be equals to the volume of this region. In other words, the overlapping volume A will be equals to the volume of the valley. However, if the overlapping volume is less as compared to the volume of the valley, in that case you will have the final bead shape or the final layer shape having a concavity like this. Although if the overlap is more, this region is more, the overlapping volume is more as compared to the volume of the valley, in that case you will feel or you will find a bulge kind of shape at the top. So the optimality is when the overlapping volume and the volume of the valley is equal. So let us try to find out what will be the step over in that case if we consider that the volume of the valley is equal to the volume of overlap. So what you are seeing in this diagram, there are two beads. One is this and second is this. The width of the bead is W, that is the distance from here to here. Also, the distance between the center of the two deposited bead is given here by P. Why P? Because sometimes we call it as pitch as well. The half of this distance from here to here will be P by 2, and that will be nothing but at the intersection of the two bead where they are intersecting. Also, this distance from the center to point F will be nothing but half of the width of the bead, that is W by 2. Now we are claiming that the area which is represented here by HGJ, or let me just hatch it, HGJ, this area should be equals to the area EFG. So this is the area EFG. Also, the area HLG, as this is the center line, the area HLG will be equals to the area EIG, that is this much. So meaning to say the half of this area will also be equals to the half of it, because they both are, there is this particular line is dividing this area in two halves. Also, as this area EIG is equals to IFG, then I can replace this from this equation and I can say the area HLG is equals to area FIG. So let me highlight the two area which I am talking about. So I am saying this area, now this area, that is HGL or HLG, will be equals to the area FIG, which is here. If these two areas are equal, then definitely you will be having an optimal step over, and as a result you will get a flat shape or the flat top on the overlapped area. So for that, let us find out the area HLG and area FIG. So to obtain the area HLG, I can do the double integration, right? So that will be starting from this point 0 to this point, that is P by 2, right? So integration from 0 to P by 2 for the x-axis. So integration from 0 to P by 2, and then from this equation to this equation. So this equation is nothing but y equals to h, because this is the height, this is the equation of this line, and this is nothing but the curve y, right? This is nothing but your curve y. So we are integrating from this curve to this curve while restricting our integration from 0 to P by 2. So 0 to P by 2 in the x and in the y from this curve to the top curve, that is y equals to h. And dx dy is an element taken at a distance from here. Maybe I will take a small element at a distance, that is the dx, having the dx width and the height dy. Now in a similar fashion I can find out the area of this curve as well. So in this case I will integrate from this point, that is nothing but the P by 2, this point is at P by 2, right, that is x equals to P by 2. I am assuming my coordinate system here, that is the center of the first bead. So, this is x equals to P by 2 and this one is x equals to W by 2. So, integration x equals to P by 2 to x equals to W by 2, and then integration from this line, that is nothing but y equals to 0. So, y equals to 0 to this curve, that is y. I am writing here just the curve y. We know that this curve y is nothing but the shape of this parabola, which we have already derived, and the equation of that was something like this, that is y equals to h 1 minus 2x by w square, as you are seeing here. So, now I can replace this value of y in this equation and further I can do the integration. After simplification, I will be able to obtain this equation, and now after putting the limit also, the final expression, and then after putting the limits also and further solving it, I will obtain the value of P, that is nothing but the pitch or the distance between two subsequent beads, or also called as step over, equals to 2 by 3 times of the width of the bead. Width of the bead is nothing but from here to here, that is W. So, this is the optimal value. Therefore, we can say that in order to obtain the almost flat surface while depositing in the XY plane, the distance between the two consecutive beads in the case of wire arc additive manufacturing should be equals to 2 by 3rd of the width of the bead deposited. Of course, there are several assumptions we have made, but still this works very fine and gives us good results. Now, let us try to solve an example. It says, in a MIG welding based wire arc additive manufacturing process, the following process parameters are considered. The first one is the torch speed is 800 mm per minute. Torch speed I will represent by Vt. The bead height, which is h, is equals to 2 mm. Penetration depth, which is the depth of the penetration into a substrate, is 0.5. Diameter of wire is 0.8 mm. The current, welding current I is 100 amps. The material density is 7.8 gram per cc. Efficiency of the process is 90%. Now, for this process, it is asked to calculate the following 4 things. One is, what is the deposition rate in gram per minute? Second is, what is the bead width? What will be the optimal value of the step over? And finally, they are asking us to calculate the approximate value of the minimum required power. Of course, there are some assumptions given. It is said that assume the bead cross section as parabola. Consider the given diagram for wire feed, speed and current relation, and also consider the following material property, such as the value of Cp, melting point, room temperature and the latent heat. Now, let us first find out the deposition rate. So, the deposition rate can be found out from 2 ways, either from the wire side or from the deposited bead side. So, if we are considering the wire side, so the deposition rate dr I am writing as will be equals to the area or the cross sectional area of the wire multiplied by the speed of the wire by which it is coming out of the nozzle into the density of the wire. So, of course, the area of wire is known to us because the diameter of the wire is given and the diameter of wire is 0.8. Therefore, I can easily find out the area of the wire, and area of the or the cross sectional area of the wire will be pi by 4 d square, and as a result it is coming to be pi 0.6 times 10 to the power minus 6 meter square. That is the area of the wire or the cross section of the wire. Now, the torch is moving with the speed Vw. Now, how do we obtain this Vw? It is not directly given to us in the problem. Instead, the current is given to us, and they said that the current is 100 amps. So if the current is 100 amps, let us go back to this diagram, and you can see if the current is 100 amps, then correspondingly the wire feed should be 8.4 meter per minute. That is what given in the diagram. So once I know the velocity of the wire also and the area or the cross sectional area of the wire also, I can easily find out the deposition rate. So the deposition rate will be equals to area of the wire into the velocity of the wire into the density. As a result, after solving this, we are getting 33 gram per minute. So typically in the case of wire arc additive manufacturing, the deposition rate can go up to 50 gram per minute. This is the only process which I know can deposit with a very high deposition rate and really builds the part with a very faster rate as compared to the any other additive manufacturing process. However, of course, when you are depositing with a very high deposition rate, you will compromise with the accuracy, and as a result you may need some post-processing operations such as milling. So that part we will discuss later. Now let us move to the second part of the example, that says what will be the bead width. So we know the height is given to us, and it is also said that assume that the bead profile is parabolic. So if it is parabolic and given to us the height of the bead, it is asked to find out just the width of the bead. We have already derived this equation by equating the mass flow rate, and it is coming to be the width of the bead should be 3 pi VW into dW square divided by 8 HVT. We already know all of these parameters, like wire feed rate we have already calculated from the chart, and it is coming to be 8.4 meter per minute. The torch speed is given to us, that is 800 mm per minute. So in meter if I am writing, it is 800 into 10 to the power minus 3 meter per minute. Height of the bead, that is 2 mm is given to us, and in meter it will be 2 into 10 to the power minus 3 meter. Wire diameter is 0.8 mm or 0.8 into 10 to the power minus 3 meter. Putting all these values into this equation, we will obtain the width of the bead to be 0.0039 meter, and in mm it will be 4 mm approximately. So that is the approximate value of the bead width. Once we know the bead width, we can easily find out the optimal distance between the two consecutive depositions. So this is for example bead 1 and this is the bead 2, and the distance between their center is given by P. So we already derived that. In order to obtain a flat surface of the overlap area, the P, this pitch or the step over should be equals to 2 by 3 W, and W is also known to us now, that is approximately 4 mm. As a result, the step over should be 2.64 mm. Now the last part of the question, that is asked, where it is asked the minimum required power. So what is known to us is the cross section of the top bead. It is asked that assume that it is parabola. Let us assume that the penetration is also represented by a parabola, and the depth of the penetration is given to us, that I am writing as Pn, and it is 0.5 mm. Once I know the depth of the penetration is 0.5 mm, then I can easily obtain the area of the same. So in both the cases, the area of this top bead and the bottom, as both are parabolic considered, will be equals to 2 by 3 height into the width. The height on the top bead deposited is 2 mm, while on the penetration side the height is 0.5. So for both the cases we know this area. Now question is how to find out the energy. So the energy required for melting the wire and energy required for melting the substrate, if we sum these two, we will be able to find out the total energy required. So the wire which is coming from the top, we know its volume flow rate, and we have to melt this also, as well as at the same time we have to melt the substrate also to get this much penetration. So this simple energy equation can be used here, that says the mass, that is m dot, because I am trying to find out the power, so this is m dot, the mass flow rate, and it will be nothing but, and this is nothing but the mass flow rate of the wire which is coming from the top. I know the cross section of this wire, I know the velocity also of this wire, and I know the density also of this wire, hence I know the mass flow rate. So, mass flow rate is rho AW into VW, that is the area of the wire into the velocity of the wire, into, so this is nothing but m dot bracket Cp delta T plus latent heat, that is L. Again, now the energy required for melting the substrate can be given like this. We are moving on the substrate with the speed of Vt and getting this much penetration on the substrate. Therefore, the cross sectional area of the penetration, that is AP, it can be calculated by 2 by 3 multiplied by height of the penetration, that is 0.5, or the depth of the penetration, that is 0.5, into the width, that is 3.96. So, that is the in mm square the area of the penetration or the depth of the penetration. So, this area multiplied by the traverse speed, that is Vt. So, this much mass, if it is multiplied by rho, so this much mass per second will get melted when we are traveling in this direction, and as a result m dot Cp delta T plus latent heat will be nothing but the energy required to melt the substrate. Now, we will put all these values here because everything is known to us, and further after simplifying we are obtaining the power equals to 731.14 watt. Also, I missed that the efficiency is divided here because it is given that the efficiency of the source is 90%. Therefore, we have to give slightly higher power of what we are calculating, and that will be divided by the efficiency. So, as a result, the required power is 731.54 watt. So, other processes we shall discuss in the coming lecture. With this, thank you very much.